Morena koutou katoa, ko Jason Ingham aho. Welcome to the first plenary session of the conference. So let's get into it. First up is Stuart Oliver. Stuart is Technical Director of Development at Holmes in Christchurch. Stuart has over 20 years of structural engineering experience working in New Zealand, Europe and California. He is a lead author of the MBIE Technical Guidelines on Seismic Assessment of Existing Buildings and is part of a MBIE working group developing low damage seismic design guidance material. Stuart's professional interests include performance-based seismic design, the use of digital technology in the AEC industry, and promoting community resilience and functional recovery. Thank you, Stuart.
Thank you, Jason. Right, this morning I'm going to give you guys an update on the low damage seismic design project we've been working on. But first of all, I was going to give Katie Simons from MB a brief bit of time to talk to you about her involvement in the project and what MB's doing.
Thanks, Stu. Hello everyone, my name's Katie Simons. I'm Principal Advisor Engineering within MB, and Stu and Paul have kindly let me kind of gate crash the presentation a little bit, partly to sort of introduce it as an MB project, a really important project, and we're really looking forward to seeing the results from the team led by Engineering New Zealand. But I just wanted to use this as an opportunity to maybe introduce the team at MB, because we've already heard a lot, MB in the first, we haven't been here very long, and MB's come up quite a lot. And I just wanted to kind of outline who, when we talk about MB, who the relevant people for you guys are. So this slide is kind of sort of where we see ourselves fitting. So we've got the New Zealand construction sector, pretty big, really important sector for New Zealand. Within that, the central regulator for that sector, the building regulator, sits within MB, which is a huge organisation, the largest government ministry by far, 3,500 people employed by MB. They're not all working on the building code. So within MB, we've got the Building System Performance branch, and that branch is where the building performance logo that you see up here. So the sort of brand of our branch is Building Performance, and our general manager there is John Sneed. And that's about 120 people working on in the Building System Performance branch. And then within that branch, the team that I sit in is called Building Performance and Engineering, or BPE. Quite good at TLAs in government. So the BPE team is the technical team within the Building System Performance branch, and we essentially look after the sort of technical content of the building code. There's about 20 of us in that team. So going from MB, 3,500 people, to about sort of 20 of us in the team, the technical team within the building regulator. And for those of you who might not be aware, our manager, we've recently had a new manager appointed, Jenny Tipler, so she's stepping up from managing the half the engineering team within that team, so she is now going to be managing the building performance and engineering team when she comes back from leave in August, later this year. And just also a quick plug, the chief engineer role, some of you may be familiar that has been a role, but it's not currently occupied at the moment, but just to confirm with you that will be advertised. The decision's been made to sort of revamp that role. It's going to be a joint role funded by EQC, but it will be a full-time role contracted within the Building System Performance branch. So do keep your eyes out for that in the next few weeks. That advert should be going up soon. But I'll leave you, thanks, to talk about this project. Thank you.
Thank you, Katie. Right, so this morning I'm going to talk to you guys about the low damage seismic design project, which is part of the MB program, the Tukahikatea Building Resilience program. It's been deliberately given a te reo name to reference New Zealand. It's similar to, but different to, other building resilience programs developed in the US, such as READY and the USRC, or the US Resiliency Council scheme. We referenced the Kahikatea tree, and if I'll let you read that text. Cool. So, as Katie said, this is an MD-funded project, and it's been project managed by Engineering New Zealand. For the project, we're adopting an iterative and collaborative approach. Most of the content is being developed by the working group, and that includes representation from architects, structural, geotech, mechanical services, fire, and facade engineers. And that's principally because low damage seismic design is not a structural engineering problem. I'll repeat that. Low damage seismic design is not a structural engineering problem. And it's a whole building issue, so we're getting input from everyone. That's relevant. And we're developing this content with our audiences, and that's building owners, people like yourselves and others, to ensure that the content which we deliver is what you need. So we're keen to get feedback on this. We've got a pretty significant technical review team, which consists of both international and national experts. We're testing the content with our clients, as well as the various different technical societies. And we've got a governance structure with representation from the main stakeholders you can see there. That's kind of the organisations in terms of the who. This slide identifies the key people involved in the project. As you can see, we've been very lucky to get the best of the best in terms of the New Zealand building industry, plus a number of international experts. Cool. Sorry, time's a bit short this morning, so you guys have to do some reading as well as me talking. Right, the project objectives. We've drawn this graphic as a set of stairs, and that's because we're after a fundamental step change in behaviour. So the primary objectives are to develop a common language which we can talk about low damage design when we're discussing it with our customers and other consultants. There's going to be more of a detail around the philosophy of low damage structural design, the benefits of it and the trade-offs associated with using it. There's going to be a technical definition of what low damage design actually is and how you as a design professional can achieve it in your projects. And there's going to be supporting material which you can use to have conversations with your clients and other design professionals. And in addition to this, the project is foundational to longer term aims, which include increasing market demand for more seismically resilient buildings, normalising low damage design in practice, and easing the way for future changes to our building regulations. Outputs from the project include support materials for building owners, users and tenants, advice for design teams, and targeted information for different audiences. For example, we're developing content for boards to help them evaluate business cases where they might be considering low damage design. In terms of this morning's presentation, we're going to focus on the top two, which is the content being developed for our customers, and a reflective brief the design teams can use when speaking with their clients. And Paul will also be briefly touching on suggested performance objectives. This slide here outlines the typical design and return briefing process we're recommending. Essentially, first of all, we need a client that wants a building, and then that client needs to decide if he wants seismic resilience or not. Then early on in the design phase, once the design team has been engaged, that design team needs to have a discussion with the client, and hopefully through the use of a reflective briefing process, which I'll talk about shortly, they can agree on what the low damage seismic design performance objectives are for their project. And then outcomes from this process then need to be translated into a set of technical design criteria the design team can use. So these are the three sets of information that are being developed for building owners, users and tenants. The key thing is that they're written in plain English. Our clients aren't structural engineers. They don't really care about structural engineering. They just want to have a good building. So these documents are intended to help clients decide if seismic resilience is a goal for their project. In plain English, they explain what low damage seismic design is, the benefits of low damage seismic design over code minimum, and also clarifies what percentage MBS is, which is always a bit of a bugbear. It also includes a briefing guide, which I'll go into in a second. Right, the briefing guide. Here it is. The key objectives here is to educate building owners, users and tenants so they understand the basic concepts of what low damage seismic design is. And this is really important because often things like site selection are made before, decisions on site selection are made before the design team is engaged. And what we have learned as part of our experience over the last few years is that if low damage seismic design is going to succeed, you need to think about it early. And so going back to the whole site selection dilemma, there are some sites where low damage seismic design won't work or it's uneconomic to work. You might have a site which is prone to liquefaction, lateral spread, you might be in a tsunami zone. And really, you're better off putting your building somewhere else if low damage seismic design is something that you want to do. The briefing guide also contains a discussion around other topics such as building form, occupancy and use, the contents and how valuable they are. And it's all written in plain English so your client can have a think about all these matters before they even speak to a QS or an architect or a structural engineer. So once we have engaged a design team, the next thing the design team needs to do is have a discussion with their client to understand what the client wants. So that's really important because it's their building. And to help with this task and these decisions, we are developing, as part of this documentation, a series of topics for discussion to help establish what our clients' needs are in terms of the seismic performance of their building. So these we'll be asking questions such as, here's some examples here, what is the building going to be used for? How important is it for you to get back into your building straight after an earthquake? What sort of contents does your building have? Are they valuable? Do you have other buildings you can use? And those sorts of things. And then once you've had these discussions with your clients and got their feedback, you can then turn this into design parameters which the design team can then use to design the building. And I'll hand over to Paul for the next slide. Thank you.
Yeah, thanks, Stu. Game of two halves, we're just at half time. So, having had a discussion with your client and we are suggesting the types of questions you might like to ask your client, because that's in plain English, we then need to turn that into some agreed design parameters. So again, the documentation's coming up with some suggestions. That's not an exhaustive list, that one, that's just a sample of what we've got. But, things like what's your SLS1 load case, SLS2, that sort of thing. And what we're doing is we've suggested a table where you agree the level with the client that they want, but we've also put some benchmarks in there. So this is all predicated on the fact that, and I'll talk about this in a minute, the performance continuum is just that, a continuum. So there is no right or wrong answer, provided you're above code minimum. So you might select things for some clients that other clients wouldn't select. So again, it's just about breaking it down, and it's not about low damage design structure, it's about low damage design for the buildings. So we've deliberately split it in there for envelope, building services, etc. And it may well be, much like we have capacity design concepts, there might be some things that your client is actually prepared to sacrifice in terms of performance along the way. So, you might have some sacrificial partitions or something like that in the building. Suggested performance objectives. So before I get into what we're currently suggesting, just the philosophy is, in terms of safety, that's addressed by the New Zealand Building Code, and we're not going there. When it comes to damage and recovery, so again, going back to the plain English, we're actually defining damage in terms of insurance terminology. So we've got a estimated or expected annual loss, and as one of the measures, and we've also got, at the moment, we've nominated a 5% threshold of damage of replacement building cost, and these are probabilistic values. And then we're talking about recovery time, and that even gets a little bit more sort of probabilistic, shall we say. Flash this slide up there, not really wanting to spend too much time on it, but knowing engineers want some of this detail. So whilst we're focusing this talk on the client-based document, in terms of the current suggested performance objectives, we've got this notion of good, better, best in terms of a continuum, and we are testing at the moment against certain return periods. It is important to note that we've introduced a new limit state called the damage control limit state, which is the DCLS. The figures that we're nominating there are not magical figures. They're actually in the Ministry of Education structural geotech requirements in terms of return periods. So we've just used those as a placeholder at the moment. So where are we at now in terms of the project? So we're about to embark on a benchmarking exercise. So we've got most of the way through a lot of the work. And we sort of paused going, okay, we've chosen these performance criteria, but how do our building stock actually perform against them? So the concern was we're walking a tightrope between a stretch goal that's achievable and actually turning the client community off going down this low damage path because it's just too hard for them to achieve it. So what we're doing is we've got a performance continuum, and I've got a slide on that next, that we effectively want to run some buildings past that have currently been built, and we're trying to select buildings that the design team or the client team are saying are better than code performance. Now, whether they achieve full low damage or not, and we just want to see where they fall on that performance continuum to know whether we've got the settings about right or whether we need to tweak them up or down a little bit. So what the scope of the project is, we're going to sort of select 15-ish buildings. We're going to come up with a questionnaire. Going to ask the design teams to fill the questionnaire out. We'll probably have a conversation with them, and then we're going to document those observations. We're going to nominalise the buildings, and we're going to prepare a little bit of a summary report. So big bold red lighting down the bottom, we need your help, please. If anyone's got any buildings that they know of that are complete, that they've been involved in, where the client and the design team's aspirations were significantly better than code, or at least above code, and you think your building will be a great case study, please come and see Stu, myself, or any of the Engineering New Zealand team, and we'd be delighted to have a further conversation with you about including your building in the study. So again, in terms of the benchmarking, what are we benchmarking it against? This slide really just shows the continuum that we're talking about. So notion of good, better, best. When we first started, we sort of just hit the better one, but then we've tapered the continuum to go either slightly below or significantly above, as the case may be. And again, same as before, what we're doing there is we've suggested some return periods that we're going to call the damage control limit state. Those return periods are nothing more than the placeholders out of the Ministry of Education guidelines, and that is all, I've got to stress, this is all very much work in progress, but this is what we're going to test the buildings against. Depending on the outcome of that study, we may tweak these up or down or leave them as they are, we just don't know yet. Next steps. As I said, the benchmarking. Please, if you've got any buildings out there that you would like or think would make a good case study, we'd love to hear from you. Otherwise, we're probably going to just try and shoulder tap people. That bench study, the plan is to deliver later this year. At that point, that'll give us a steer on where we are in terms of our performance continuum, how much rethinking or not we need to do. Once we've got the benchmarking and understand where our performance continuum sits, we've got to finalise the documentation, and then really importantly, we've got some world-renowned experts, so we're going to do a peer review and we're going to test with stakeholders. So that's effectively the 3 documents that Stuart talked about at the start. So that's the building owner stuff, it's the design team stuff, and it's the more general brochure type stuff. So assuming we get the big tick on all of that, the goal is to publish next year. Not yet sure, depending on how the peer review process and all that goes, the form of that publication. So we've got a whole myriad of options in front of us. We might be publishing all 3 documents at one hit. We might publish some ahead of the others. Some might come out in draft. Not sure. Watch this space, but the target is next year because we realise the industry wants it. And then a really, really important piece, it's not publish and walk away. There'll be a training and education program following that. And my very last slide is to just let you know the depth and breadth of horsepower that's brought to this, and to acknowledge all of the participants. So all of those people are involved, and their input has been fantastic. So thank you.
I actually have a question of my own, first of all. I assume there's a conference paper with this, but if anyone wants to do any reading on where the interim state is there a website to pull some stuff off, or is there nothing really available?
Is the short answer. Yeah, we're in a little bit of a hiatus, but look, come and see us if you've got a burning question, and we'll do our best to answer.
Okay, so we still have about 3 minutes. You know the protocol. Oh my gosh, okay. Might take a double throw. I'm coming in this direction, so here we go. One row back.
Is it on? Yeah. Paul, the stated performance requirements at SLS1 are
Yes.
a little unclear, but it appears to be saying you can accept having to do repairs at SLS1. That is what is in the Ministry of Education Seismic design document. That is an incorrect interpretation of the building code. At SLS1, the requirement is no repairs.
Question or statement?
Statement.
Fair enough.
Okay, any other questions or statements? Oh yes, have to chuck it back behind you. All good stuff.
Great. Yeah, thanks for the presentation. Has thought been put into bringing in the likes of, say, you've got QuakeStar or the US RC rating system, and how that might be applied to the document that you'll release?
Yeah, so Stuart sort of, in the interest of time, has sped over that. We've looked at both the Red Eye system and the US Resiliency Council. Out of scope was a rating system, which kind of parks some of the US Resiliency stuff, council stuff, and and also some of the Red Eye stuff. But more importantly, they're morphing into shelter in place. So what we've done is we've done it slightly different in terms of coming up with an agreed level of damage in terms of a repair cost. And then, as Stuart said, part of the Te Reo lens that we've put over this is we want it to be uniquely New Zealand. So I hope that's kind of answered your question. There are some subtle differences, but we are relying heavily on those 2 documents where it makes sense.
Could I ask everyone to thank our speakers one last time? To stick on time, I'd now like to introduce our next presenter, who is Nick Brooke. Nick is an Auckland-based structural engineer and principal at Compusoft Engineering. Nick is actively involved in research, including the ATC 145 and Recast Floors project that he is presenting on at this conference, and in continuing efforts to improve assessment guidance for concrete structures. Nick is currently the Vice President of SESOC. Thanks, Nick.
Thanks, Jason. And it's almost like Carl's done some planning on the presentations here or the program. My talk now sort of segues quite nicely, I think, from what's just been discussed. So this ATC project is an overall project, very large US-funded project, focused not on how to make future buildings more resilient, but what happens when you have an earthquake and how you assess the resilience of the structures you've already had and what needs to be done to them. It's a large project, as I've said. The main project technical committee's listed up on the screen, and I think that's probably actually last year's working group. So in addition to the technical committee, there's all sorts of student involvement and others doing a lot of work. We're in the third year at the moment, and I'm basically talking about work from the previous year. But in terms of trying to fit it all into a presentation, we've got 3 years of stuff. The conference paper condenses about 300 pages of report down to 15, and now we're trying to fit that into 15 slides. So hopefully it all hangs together. It has to be emphasised that the focus of the work in this paper is really around ductile frames. The overall project is looking to have a broader focus. FEMA, who are funding the majority of the project, basically want guidance on what repairs are required and what you have to do for any type of building. But obviously that's a pretty big apple to take a chunk out of. And so to try and make things a bit more manageable, the project brought its focus back down to a more well-known type of system to try and develop some processes that hopefully we can now expand back out again. And being a US-centred or centric project, they've got the fortunate situation of not having so many precast concrete floors to worry about. And so all the conclusions and all the discussion in here really needs to be caveated that you're probably going to have to overlay a lens of precast concrete floors if you were trying to apply this in a New Zealand context. So I guess if we're trying to set out an overall premise for where the project's come from, or what this process that I'm talking about today came from, it's probably that if you have an earthquake, then obviously some buildings get damaged. Hopefully none of them collapse, but you may have some collapses. But some buildings will be very lightly damaged, or even not damaged. And if you particularly are in a context less fortunate than New Zealand has been of not having so much insurance, then you're going to have a very large number of buildings and a relatively small number of engineers available to work with those, and we're obviously still dealing with earthquakes 10 years after the fact, and things could be a lot worse in some of the big US cities, I guess. But you're also going to be dealing with situations where a building owner maybe is having to dip into their own pocket for whatever reason, and so there'll be very real questions of, sure, the building's damaged, but does it actually need repair? Or is it an urgent repair? Can you use the building in the interim, and so forth? And I guess you can contextualise it that a lot of us have cars with a few dings and scrapes where they get parked a bit aggressively, and you obviously don't necessarily rush off the next day and drop everything to fix all of those. There's some sort of judgment made about whether the repairs are urgent or not. And so what's been developed is an assessment framework, and some of this will probably to some of you seem like we're teaching you to suck eggs, and it's really in many ways formalising the sorts of things that to greater or lesser extents have been done in New Zealand over the last 10 years, working through inspections and analysis of buildings, and then working out what needs to be done on the back end. And a feature of the project, I'm afraid, is that there's a lot of these sorts of flowcharts, and I understand that these will be pretty hard to read on screen, so I've tried to sort of précis them and pull out the key points. Also need to emphasise that a lot of these are sort of the version 1 flowcharts, and in the documents that we've got floating around in the project now, there are refined ones and often simpler ways of looking at the same project, but in deliberating what to put in the presentation, I've stuck with the ones that are in the paper, mainly so that I can say to you, don't worry about reading these, they're in the paper, but there will be, there are improvements existing at the moment, and over the next however long, you can expect ATC and FEMA to be releasing reports with better versions of these in. So we've basically got a 3-step process. We'll talk through those: inspection and analysis, followed by a compulsory safety assessment, or compulsory if it's required, I guess, and then an optional serviceability assessment. And that serviceability assessment is interesting from a US perspective. I hadn't realised that they don't actually really consider serviceability earthquakes in the design of their buildings, and so there's sort of treading on eggshells a bit to make sure that you're not putting an onus on building owners after an earthquake that was probably never there when they were actually consenting buildings in the first place. You obviously need some objectives with any assessment of a damaged building, performance objectives, or what a repair is trying to achieve if a repair is required. And so the project set up these 2 objectives here that essentially have unchanged performance in a future large earthquake, so the building's roughly or approximately as safe as it ever was. And then from the serviceability perspective, something that in a New Zealand context is probably reasonably obvious, that you'd be looking for a building to be able to withstand a serviceability earthquake without sustaining any major damage, being able to be used and probably being largely undamaged. But as I've sort of alluded to, in the US context, that introduced a whole load of question marks because they don't even actually define what an SLS earthquake is in terms of return period and so forth. Now, the bulk of the presentation here today, I think, is really focused on the inspection and analysis phase. Some of you will have seen the presentation I gave at the NZSEE conference that focused on the safety assessment phase, and I'll reference that again later on. But really here, I think we're talking through what is kind of a looping process of inspections, followed by analysis to work out what's going on with the building, using that analysis to inform further inspections, and working through until you've got comfort that you have an analysis that realistically matches what happened in the building. It's not to say it's an absolute forensic perfection of knowing the rotations at every single joint to the nth degree. It's a sufficient match for what's required, and we'll talk through a little bit more on what that might mean. And not so clear from these flowcharts, and it's something being emphasised in the newer versions, the concept of easy outs exists as well. And obviously everyone's been to a building, maybe one you think is going to be likely to be quite damaged because it's an older structure, and you look at it and go, well, for whatever reason, this building's pretty obviously no worse off than it was prior to the earthquakes. And in that situation, you obviously don't want to be spending a whole load of time and resources, both in terms of the owner's cost and potentially scarce engineering resource, crawling over every inch of a building that really doesn't warrant it for that purpose at least. For the ATC project, the inspections are given 2 purposes. There's the obvious one of looking for severe damage, which everyone will have been doing anyway, and things that obviously necessitate repairs. So if you go to a building and find that half the columns have shear failures, then you probably drop out of the process of do you need repairs and start thinking about how you might do it. But then in terms of the broader concept of you've got a building that's likely to moderately damaged and a question of does this need repair, then the inspections are going to play a really important role in calibrating whatever analysis you have. Because really the aim of the analysis is to get a feel for how far the building's moved and what that's going to mean for it. And so to have confidence in that, you need to know that your prediction of 1.5% drift, or whatever the number might be, matches up acceptably well with what you're seeing on site. The analysis is set out in a framework that ties in a lot with ASCE type documents, and so in the paper there's a bit more discussion about linear dynamic procedures and non-linear static procedures and so forth, with the obvious overlay that the analysis that you use for a particular building will be informed by what you see with the building. So if it's a simple structure with very minor damage, then a linear analysis might be perfectly acceptable, or even we've heard this morning about hand analysis already, and that could be sufficient to give you comfort on what's going on. On the other hand, if it's a complex layout and plastic hinging here, there and everywhere, then you'll probably need something much more sophisticated to get a handle on what's going on. And one of the key challenges is going to be how to represent the likely earthquake shaking. We've been pretty fortunate so far in New Zealand to have dense arrays of strong motion recordings, but the project's had to consider situations that exist in most of the world where maybe you've got a recording within 10 kilometres, maybe you don't, and what sources of information exist for that, and how that might change heading into the future. And the key output from the assessment and analysis phase really is to identify what the likely deformations in the building are. The primary indicator is probably the drift imposed, but depending on the way that the assessment phases go, you might be looking at chord rotations and critical beams as well. So criteria that we're fairly familiar with from assessment processes and general engineering. And as I've already said, you really need some confidence that the estimates that you're getting are realistic. They don't need to be perfect, and the level of perfection required depends on whether you're close to some threshold values that exist in the assessment processes, but you're going to need to try and tie them to what's seen in the building. You might be using crack widths. There's a bit of caution required there, obviously, an understanding of what's driven the cracking, the axial load that might have caused closure of cracking or might not, depending on the situation. And the other thought that's fairly appealing is use of existing fragility information. So you might have a jib partition wall running up your stairwell and know that that has a certain probability of being damaged for a certain level of drift. But there is some challenge in that as well. One of the project team described it quite colourfully as trying to pour water through a funnel backwards. And you sort of end up in a situation where a certain observed piece of damage can have quite a wide range of interpretations. So it really needs to be quite a holistic look at the building to get a feeling for what's happening. In a lot of circumstances, the situation's not going to need to be resolved to a high degree of accuracy. So we'll talk briefly in the safety assessment phase that for ductile frames, 2% drift is a fairly key threshold that the project's arrived at. And so if you're close to that threshold value, then you would want a fairly accurate answer. So if you think you're at 1.9% drift, then you'd probably pay a reasonable amount of attention to checking that that's the case. Whereas if you can see clearly that the building's at 1% drift or thereabouts, or at 3% drift or thereabouts, then resolving that to any finer degree of accuracy probably doesn't really matter. If things clearly don't match up, then there will be this looping process that we've talked about. A common situation, you'll over-predict what's happened. There's a lot of conservatism in many of our processes and at most steps of the analysis, and so you can quite easily imagine a scenario where the building, and it's been commonplace in New Zealand, the building's obviously not moved a lot, but any form of analysis will tell you it has, and then some less common but potentially equally tricky situations may also crop up. So moving through to the, assuming that we've got a reasonable estimate of our drift demands, you then move into the compulsory safety assessment phase. And as I said, I've talked through this in quite a lot more detail, and it's discussed in another paper. And for today, given the time constraints, it really comes down to a two-step or two alternative criteria to check. The first being for a ductile frame that if the story drift's less than 2%, and you've not got unexpected concentrated damage, so no indication, say, of a soft story starting to form or anything like that, then the future life safety performance has been assessed by the project to be effectively unchanged. Or alternately, if you don't pass that check, then there's a second sort of avenue where you can go down checking the rotations of specific critical elements and checking the condition of reinforcement to make sure that it's not fatigued or buckled excessively. And again, can get to a situation where a lot of frames with reasonably moderate levels of damage will be shown to have really no change to their life safety performance. So then finally, and within reason at the owner's discretion, I guess, certainly in a US context where there's just no real mandate for a government agency seemingly to come along and get you to check serviceability, you'd move into the serviceability assessment phase. And fairly obviously, if you impose some cracks on a building during an earthquake, then that will change the stiffness of the building. And so the aim of the serviceability phase is really to check whether that cracking needs to be repaired and whether repair of the cracking would be sufficient to restore the stiffness that's been lost to a degree that's acceptable. Noting, of course, that there may be other drivers for repairing the cracking as well, owner comfort or whatever, but this is really focused on the structural aspects of things. So as I touched on earlier in the presentation, the check basically is to look at whether a hypothetical future small earthquake, so a service level earthquake, is likely to cause damage to non-structural elements or structural elements, but obviously the non-structural is probably the focus. If it does, then there'd be a requirement or a suggestion to restore stiffness. If not, then there may have been some degradation, but the building owner can probably be happy that the building's not going to be problematic and they can really restore things at their leisure. And then I guess in common with Paul and Stu, this presentation didn't really feel like one that led to conclusions as such. It's such a précis of a large document that it's kind of the conclusions in itself. And so instead, just as a final slide, some outline of where things are heading at the moment. The processes that I've discussed are currently being benchmarked against a couple of case study buildings, that's getting towards conclusion. And then other work's ongoing to extend and improve the processes to try and bring in other structural systems. So I'll just finish by acknowledging again both the entire project team and my co-authors on the paper, and also the funding from FEMA, and then more locally and directly relevant to me from EQC for making the project happen.
Good, thanks. Nick has stuck to the timing rather well, and we do have time for a small number of questions. We've got one mic back there somewhere, and I've got another one I can place from up the front. So if anyone has a question, please raise your hand. All right, one on the corner.
Yeah, Bex, Wellington City Council. Nick, at the pre-inspection phase, and your point about the low-hanging fruit, or I think you used a different terminology, do you think there's a role for accepting sensor input with engineering assessment and not actually needing a physical assessment to be able to say, this building's okay, we can concentrate somewhere else, and how would that fit into your flowchart?
Yeah, it's a very good question, Bax, and I think certainly there is a role for it. What I didn't really touch on was that the flowcharts, or the project focuses on after the immediate inspection phase. So there are other US documents around about the placarding type approach and inspections for that. So the ATC project is premised that it steps in after that, and a lot of that screening may already have occurred. There's various things that were discussed about possibly adapting HAZUS information and that sort of area-wide thing, but I think fairly clearly there is a situation where there'd be a PGA or a spectral acceleration contour that you could say, chance of anything having gone wrong outside of this boundary is pretty small. Target the inspections inside and work outwards unless anything is obviously untoward.
Nice throw.
Hi Nick. You talk about thresholds being important, and in particular you mentioned 2% drift as being an important level, but how do you reconcile that against the New Zealand context where we know that damage to precast floors often happens a long way before a 2% drift limit? Wouldn't want us to get kind of too focused in the New Zealand context on that, given what we know about precast floors.
Yeah, no, it's absolutely right that the focus of the studies described are on the frames themselves. And so really totally agree with Hamish's comment that 2% drift, there may well be some pretty serious damage to precast floors that needs a whole load of attention. But hopefully maybe in the future we don't have quite so many of that sort of floor to deal with, and we may be heading more towards a US sort of situation where maybe 2% is all right. And it's certainly not to say the building won't necessarily look a bit uncomfortable at 2% drift, just that it's probably not, in a frame sense, it's not on average any worse from a life safety perspective. So owners may be uncomfortable being in there, but there would be no reason not to be, except for maybe the floors.
Well, good. So could I ask you to thank Nick once again for his presentation? Okay, so next up we have Professor Ken Elwood. Ken serves as Associate Director for Te Herengaru Quake Core New Zealand Centre of Earthquake Resilience, and is actively involved in research related to the seismic assessment and design of concrete buildings. Ken received his PhD from the University of California, Berkeley in 2002, and he's a registered professional engineer in British Columbia, Canada. Ken has served as a member of several international code committees, including the American Concrete Institute Building Code ACI 318. Thanks, Ken. Over to you. You got 15 minutes.
Thanks, Jason. February 2020, a good mate of mine, Gilberto Masqueda, was visiting, and we were tramping on the Alpine crossing. And we were trying to come up with a way he could come back roughly a year later. He's an expert in base isolation. I'm not. And we thought, let's do a project together on base isolation. And you can come back and you can give the talk. Shit. Anyway, so here I am, and I am not an expert in base isolation, but I've learned a lot about it through this project, and it's been really, really interesting. You might be asking, why are we doing this? Why are we looking at base isolation in Wellington right now? Isn't that the gold standard? Shouldn't that be the answer? Well, there's been a lot of recent literature that's shown that base isolated buildings, when they experience larger than expected events, so larger than your design level considered events, can actually have a lower collapse performance than an equivalent fixed base building. And so this has caused some ripples in the base isolation industry, and it started me thinking in the Wellington context that we know in Wellington our hazards likely going to increase. We also know that the National Seismic Hazard Model is going to come out with not just a single hazard value, but a range of values. So we're going to need to be prepared for those larger than expected events, if you will. And we also know that many of the base isolated buildings, well, some of the very first base isolated buildings in the world are in Wellington. And so they've been designed prior to the NZSEE guidelines of 2019. And so they may have smaller moats. They will have smaller moats than what those guidelines require. So we need to understand what is the performance of these buildings if we see these larger than design events. And look, I'm not trying to do to base isolation what we've done to hollow core. It's not the same. But I think it's important that we understand what these gold-plated systems will do in these large events. So Here's a map of what we think are all the base isolated buildings in the CBD. Got another 3 outside the CBD. And there's a range of moat clearances shown up there, for the lowest being 250 in the Ministry of Justice. A typical moat clearance, though, across these buildings is about 600 millimeters. And I'll come back to that number in a moment. And we considered what is the ground motions that we should be considering for Wellington. And we took the approach that the National Seismic Hazard Model is now following. This is not the National Seismic Hazard Model, but it considers multiple ground motion prediction equations, which give us, instead of one hazard curve, basically give us a band of hazard curves. And here we're really interested in the big events, okay? So our MCE. So if you look there at 2475, and these log scales that seismologists love, it's actually over a factor of 2 from one end to the other of that band. So we need to consider a range of ground motions at that level. So we chose 11 motions to match 2 spectra, one which was the median 2475, and the other was a 90th percentile 2475. So these are big motions, big motions. Okay, we chose 11 motions, matched them to those spectra, and we'll use those 2 sets as we go through here today. And by the way, we did all the same thing at 475 or 500 year, and they performed beautifully, as we would expect. So let's just focus on the 2475. Here's our building model. And this is a sort of an exploratory study, if you will. So our building model for now is simply linear elastic, and 5 stories on base isolators, which are modeled using this hysteresis shown there. But the important part of our study was this: what happens when it hits the moat wall. And so my friend from University of from UCSD has done a lot of work on this, and what sort of effect that pounding has, and how do you model that pounding with the moat. So they've developed the model shown here, so we incorporated that as well. I'll come back to the fact, bear in mind that everything I'm going to show you here is a linear elastic model for the building itself, because that's how we would like to see our base isolated structures mostly perform. I will come back at the very end if I have time to talk about if it is a nonlinear model. And then reflecting on the guidelines from NZSEE, or draft guidelines for base isolation, we identified that there's a category of a 4-star rating and a 5-star rating. We called the 5-star rating our post-guidelines buildings, because I think that's what they're really recommending that one targets. And the 4-star rating is like our pre-guideline building, where our moats really aren't quite big enough. And so the 4 cases that I'm going to consider here are 2 cases with a moat that is that meets the NZSEE guidelines, and then 2 more cases where the moat is roughly equivalent to the average moat that's in Wellington base isolated buildings right now. And for each of these, I'm going to consider the median hazard and that 90th percentile, that really big hazard. Okay, so first of all, the question is how many impacts do you get? So case 1 was that the NZSEE guidelines moat of 800 and the median seismic hazard, and no impacts. Good news. What if we push that up to the 90th percentile seismic hazard? Now we've got 3 of our ground motions producing impacts. So still not too bad, but we've got to deal with those impacts. What if we go down now to the 600 millimeter 600 millimeters, now we've got 4 producing impacts, some of those producing multiple impacts. And finally, if we go down to the 600 millimeter moat, but give it that big ground motion, 90th percentile, now we've got 9 out of the 11 motions producing impacts, some of them many, many impacts. Now, what does that mean? Like, so what if there's an impact? What does it mean? And so we're going to capture that in terms of the impact velocity. How hard is it hitting? If it just touches the moat, that's not a big deal, right? It's when it hits it hard. So again, case 1, of course, there were no impacts at all, so no worries there. Case 2, we've got a little bit higher, and at least 1 there going above an impact velocity of 1 meters per second, which I'll use that as a benchmark in a moment. And then as we go into the smaller moat, we start to see multiple impacts for each of these ground motions hitting. And when we go to that small moat with the 90th percentile, we've got a lot of impacts going on and a lot of high impact velocities. Why does impact velocity matter? Well, essentially, impact velocity is going to lead to higher drift demand in the building, okay? And so in this plot, if on the left-hand side, you can see the story drift demand within the building when you don't have impact. And so those are pretty reasonable small values, which we would expect for a base isolated building. And all of the other dots there are the drift demands when we have impacts related to the impact velocity on the x-axis. So you can see as the impact velocity gets higher, you get higher drift demands. And just as a simple rule of thumb for you to take away here, because that's a lot of dots on the screen, is that if you have a strong impact, and I'm calling a strong impact something that's over 1 meter per second, but a strong impact, you can expect your drift in the building to be probably about twice what you would have thought your drift would have been without the impact. Okay, nice rule of thumb. Remember again though, this is a linear elastic model, so that'll probably increase. Then, of course, one of the reasons why we do base isolation is to reduce the floor accelerations, right? And all those gray lines on the far side there, those are the cases without impacts. And for a case without impacts, of course, we get very low floor accelerations. Great. And then these cases with the big spike, those are where we get impact at that level. And so we really can't avoid high accelerations where we have impact. So the first sort of rule of thumb for me would be to say, if you're doing a base isolated building, you're trying to protect acceleration sensitive equipment, you probably want to keep that acceleration sensitive equipment away from that level where you might be getting that impact. How about the stories above? The accelerations go down, so maybe they're manageable. So we'll do something similar to what we did before. Again, over here on the left side, you've got the floor accelerations without impact. Those generally are less than 0.5 g in this case, whereas the accelerations going up the building are higher if we get impact and related to this impact velocity. Again, sort of rules of thumb, roof acceleration might be 3 times the acceleration that you expected without impacts, and the first floor acceleration, so 1 floor above your impact level, might be about 4 times if you've got a really strong impact. So what to do? You know, there are all these buildings out there in Wellington that have base isolation, but with small moats. We could just try to dig a bigger moat, but that's sometimes difficult, maybe not your land. So what else is there to do? Well, what we explored was putting viscous dampers in parallel with the base isolation, and actually did a really, really, really good job. So we got in the case, in case 3 here, we basically eliminated all of the impact cases. So that was with our median ground motions. For our 90th percentile, that really big earthquake demands where we had lots of impacts, we got that down to only 2. And those 2 had pretty low impact velocities, so the impact on our drifts and accelerations was not that bad. So viscous dampers in parallel with these base isolation, older base isolated systems might be one solution. So key takeaways from my perspective: epistemic uncertainty, that's that band of the hazard curves that we're going to get out of the National Seismic Hazard Model, really should be considered when setting your moat wall distance in order to really have confidence of not having impacts. The pre-guidelines buildings are likely going to have some impacts, and particularly when we start looking at the higher hazard values expected in Wellington. If we get those impacts, we can expect to see an increase in drift demand in the building and accelerations. And I've given you some rules of thumb there, but you could see the data. It's all over the place, but it's good rules of thumb. We can use some supplemental damping to maybe bring that down. But all of this has been with that simple linear elastic 5-story model. What if we go nonlinear? And so this is quite preliminary, but simply looking at a nonlinear single degree of freedom model instead of that 5-story building, and giving it a simple bilinear hysteresis, what happens? Well, this is the case without impact, okay? And what I'm showing here is the strength of the building, okay, the base shear coefficient for the building, if you will, versus ductility demand. And you might say, well, this doesn't even have impact. What's going on? Well, what it's telling us is that once your base isolated building starts yielding, it takes off. And this has been shown time and time again in other studies. If you have impact, it takes off even faster. And in fact, may even make it worse than the equivalent fixed base building in some situations. Okay? So stay tuned. I think that's a theme of all 3 presentations so far in this session. Stay tuned as we continue this study. But thank you very much for your time.
Thank you. Now, I'm sorry we don't have time for questions for Ken, but I'm led to believe this last session is a bit of a free-for-all, and maybe some of your pent-up questions can expressed. So, I have a little blurb here. Helen is the team leader for this crew here in front of us. Helen is a structural engineer who has spent her career working in design consultancies in both New Zealand and the United States. She is the current president of the Earthquake Society and is currently leading the Resilient Buildings Project, which is an NZSEE initiative funded by the Earthquake Commission, with many across the industry involved in the project, including a number of SESOC members. And as you've already heard, other speakers have given more time to this crew so they can speak longer. So you've got the time in front of your team, you know what you're doing. Over to you, Helen.
Well, thank you all. And thank you. It's really wonderful to be able to talk at the conference today about this. So the Resilient Buildings Project is seeking to understand current societal tolerance for the impact of earthquakes on buildings in New Zealand. And in particular, if the tolerance for the impact has changed since the B1 performance objectives were set and how these expectations may have changed. So this is very much not on the solutioneering, but on the what is our clients expecting. And so what the project is doing, what we're aiming to do is to identify how they may have changed and potentially provide information that will help thinking about realigning, or if there is a need to realign the building code to better reflect societal expectations. And of course you'll remember that this is one of the recommendations that the Seismic Risk Working Group came up with last year. So we're working our way through that at the moment. And to explore this today, I thought rather than talking about the project too hard, and we'll do a little bit of that, but what I'd like to do is I want to welcome our various colleagues here, Michelle Grant, Jaden Ferner, Alex Vindell, Jarrett Keane, Nick Searle and Stu Oliver, who are going to explore this topic by talking about some building examples so that we can sort of share what our current reflections are and think about it from what we're seeing at the moment. But why are we talking about this? Well, this is one of the many headlines we saw after the Christchurch earthquake in 2011, and it was actually after one of the aftershocks, and it was a sad headline. A very newly completed building. I don't think it had even got its, it had been fully opened when this happened, but clearly this outcome was not what the owner was expecting. The question, though, and I have a suspicion that I know the answer to this, is that there was unlikely to have been any discussion about the performance expectations of the building when it was being designed or before it was being designed. We strongly suspect that the code was assumed to be, by both the engineer and the client, to be entirely appropriate. And so, of course, that's what we're trying to explore. And, of course, another topic, but we're not going to explore today, is whether the design solution met the performance objectives. And I know that's a very interesting topic, but that's going to be a different presentation or another presentation on another occasion. So that's not what we're trying to talk about today. So talking about the Resilient Buildings project, we've got some project outcomes. Our aim is to generate to have a social licence to potentially change the minimum statutory performance objectives that we have in our code at the moment. Clear shared language of desired performance objectives, and you've already heard Stu talking about that. There's a lot of work going in many different areas in that space at the moment. An understanding of the pluralities of social risk perception and how performance objectives shift and can move, and some high-level recommendations on how to form the current, how this might inform the current regulatory system for building performance. So the project is looking at it from 4 different perspectives: human, financial, social and natural. And we're currently in the process of interviewing a bunch of people and from a wide range of different aspects of New Zealand society to understand their views, and then we'll report back later with the findings. So that's where we're at the project. The interviews are underway. We're then going to run a whole bunch of focus groups. But now what I'd like to do is invite the various of our colleagues to share their experiences in talking to clients about setting performance objectives for buildings, or whether there was any discussion. I think that's one of the things we have to acknowledge. Sometimes it's not appropriate, or it's not needed, or it doesn't happen, and for a whole variety of reasons. Okay, so I'd like to hand over now and like Michelle to kick it off.
Thanks, Helen. Thank you. So I chose a simple one to start us off with a discussion. This is a new house, new residence for a client, spending a couple $1 million, and we're talking about foundations on this one. They were looking at a waffle slab, just a raft slab, an allied super slab. And in theory, that's where us engineers could exit stage left. It's a code mark type product, and as long as it's all within the technical manual, we don't need engineers for this system. But there is a conversation still to have with the client, and in this case, buried in the tech manual for this product is that if the Z factor is above 0.15, sliding's to be expected for your slab. That you're expecting that your house will slide around on the ground, in theory. So Marston and our Z factor is 0.42. So it's worth conversation with your client if they're building a brand new house and spending multiples of millions of dollars on it. Are they happy with that? Do they understand what that means? There is more robust solution if they wanted to put some shear keys in, but there's going to be a cost associated with that. So it's just a pretty simple conversation to have with them to explain, look, there's some different options. Do they understand what they're signing up for if they go with the option? It does comply to code. There's no reason that they can't do it. So it's just talking to them about what their drivers may be.
Tēnā koutou e hoho mā, ko taupuri te maunga, ko tainui te waka, ko Waikato te awa. He piko he tani whā, he piko he tani whā. Waikato tani whārau. Ki whakatū o noho ana, ko Jaden Whenui tako ingoa. Nō reira, tēnā koutou, tēnā koutou, tēnā koutou katoa. This is a commercial food production facility in Te Tau Ihu o Te Waka Maui, so up in Havelock, or down in Havelock, sorry. We got involved in it post Kai Koda 2016. It was initially constructed in the 1980s. It had a major extension, which is most of the stuff you can see was built in the early 2000s, and then we came in after Kaikoura. It's all on reclaimed land, so that all moved, and it cracked the slabs and production facility. It's got epoxy coated concrete all around the bottom, and all the shore shield cracked. But it happened late at night, so they were in their cleaning stage, so no debris got into the crack, so they were able to wash out and re-epoxy. And then as part of the things that I was the client's a national we all know that buildings are systems, so there's our part of it, but then there's everything else that goes with it, how the production goes through the plant, your HVAC, electrical, people on out, civils. For these guys to get their insurance, like the system, the structural system, they had to get 66% to reinstate their business interruption insurance. So we had to add a bit of capacity and reinstate a bit of capacity that was lost. We had to do that in the shutdown period of 4 weeks. All the internal stuff, it took a lot longer than that. But in discussions with the clients and then asking them around some of the other drivers for the project, we got talking about it, like insurance, duration of time to do the repairs, so we had to leave some repairs behind, but they were more serviceability type repairs. Like all the slab fall, even though the slab fell, all the falls were maintained, so all the drains still worked, so that met their requirement for that. And then in discussions with them on their short time frame to do the internal works, they were quite concerned about their ability to maintain their market share. And so there's things you don't really think about as an engineer until it's brought up. But yeah, it was that. So that last point, she said businesses are a system. So it's how does our structure intertwine with what the businesses are trying to achieve or our clients are trying to achieve. And as part of those discussions, we kind of got to, I know what everyone else is talking about, that's functional performance isn't just for IL4 and MOE buildings. If your clients have a process that if they lose that process, what's their impact? I think Jared's going to talk on the ability of other people that they've got capacity to shift elsewhere, but these guys, they didn't have that ability. So it was just that interaction where we're part of we think of our structure as our structure, but how does that affect our client and their system?
Good morning all. My name is Alex Findell. I'm the structures team lead here in Hamilton for ACOM. And I'm keen to describe my recent project experience where I had the luxury of having a client that was well engaged and wanting to talk around seismic performance levels. The project in particular is Rotatuna Library. It's part of a new facility being built for the new Rotatuna Town Centre. And the facility in itself is a single-storey structure. It's around 2,000 square metres GFA with a construction budget in the order of, or just shy of $9 million. The lateral load system is moment frames in two orthogonal directions. We've got reinforced concrete spread footings supporting reinforced concrete columns, which in turn support long-span glulam members. As I said, the client is Hamilton City Council, and I would describe the client as a bit of an outlier. And what I mean by that is that they are well informed. They were keen to discuss seismic performance levels, and not only that, they were willing to consider the value that designing beyond the minimum code requirements could bring to their projects. The assessment for the facility in terms of the performance requirements required us to not only consider the structural or superstructure behavior, but also the soil structure interaction. For that, we had a geotechnical liquefaction assessment, site-specific, carried out for this particular site, for which we could get the predicted settlement characteristics for the ground at the various serviceability limit state. I remembered I just jumped one thought process. Basically, it was during the early phases of the project that we actually had numerous discussions with the client around seismic performance levels. And it was at the prelim design that they actually said to us, hold on, what is serviceability limit state? And we sort of explained that what it actually meant. And they said, well, can we consider designing the structure for an enhanced level of resistance to damage for an earthquake 1 in 100 year of seismic event. And obviously what this meant was that we were going to revisit or reconsider the design for a serviceability limit state of with an annual probability of exceedance of 1 over 100 as opposed to the code minimum requirements of 1 in 25. So that's where we did our various analyses, including the geotechnical interactions. That settlement characteristics fed into our analysis of the structure and the overall behavior of the building. We were pleased to be able to report back to the client, in part due to the relative limited settlement characteristics, liquefaction settlement, sorry, of the ground, the relative stiff response of the structure, as well as the ductility that we utilized, that there was effectively no additional cost for this structure to meet that enhanced SLS requirement. Clearly, the client was very pleased with regards to this outcome and instructed us to progress with the subsequent design stages for this enhanced SLS criteria. The beauty of going down this route was that the client effectively resulted or will have a structure that can cope with forces twice that normally defined by the code, to which the building will effectively see no damage. Not only that, the statistical probability of the structure seeing forces greater than its SLS criteria over its 50-year design life effectively reduced from just shy of 90% to just under 40%. So it was an incredibly empowering and positive discussion had with the client, and it's certainly something I would encourage all engineers to do, talk about the serviceability limit state with their clients. Thank you.
All right. So I'm going to talk about two clients doing very similar buildings but with quite different approaches. So this building here, this is one of the clients. This is the Ag Research Facility that's going to be going in Lincoln University, or Lincoln University campus very soon. This is just to give a sense of the scale of it. It's as far as our clients are concerned, it's a lab building and an office building, and I'm not 100% sure they know what the structural system is in their eyes, but the other building, or the other project, I'm just going to call Project B because I can't quite talk about that yet, but it's on the face of it a very, very similar building. Also a lab for a similar sort of client, a similar sort of scale. And the difference comes in, we could have in some ways rolled out the same structure for both of these, but the clients have a very different perspective on this. So on the Ag Research Facility, We have a project-focused client team. We have a project director and a head of infrastructure who were brought in effectively for this project, and they care about making the project successful. They have very much a focus on budget. And they're very experienced individuals who went through the Canterbury rebuild. They've delivered a number of major projects and know what they're doing. And Ag Research is an organisation that has a number of large campuses around the country. And there was a very conscious decision made by the project team, driven very much by the client, that if allowed to choose the Quake hit again in Lincoln, their basic strategy was to decant people if necessary and make the most of what they could out of the building. And the discussions around resilience or low damage design on this project, therefore, were twofold. They said, as far as the superstructure goes, we'll take what resilience you can give us, but we're not going to pay for it. Which basically meant giving them a nice stiff wall building, but nothing fancy. But they were very focused on a few specific areas that were important to them, particularly their historic samples or their active samples, some of which contain things they really don't want to get out. And so they had very much a focus on making sure that the freezers which stored these samples were robust for a number of days and had backup power supplies. So the engineering of this building focused very much on the freezer continuity of all things. The other project, Project B, again, similar lab, but different individuals involved. So we were dealing there with the Chief Commercial Officer and the Chief Financial Officer, so people who are invested in the long-term life of their business and focused very much on long-term performance. They're also geographically constrained. They're in one location. And this project happened to be in key discussions about concepts, just as the news hit the media about the AF8, the 75% chance of an alpine fault rupture in the next 50 years. And it very much caught the eye of these people and of their board. And they actually came to the project saying, we're going to base isolate this thing after, aren't we? No matter what. Even if it was one story, they were going to isolate it. So it's the only time in my professional career I've actually had to talk people back from the brink of providing more resilience and low damage and suggest to them that they need a slightly more considered approach and to do something that's appropriate for the project. Maybe I'll get Ken to talk to them.
Hello. A fairly basic portal frame building, 20 metres long, 16 metres wide, used for retail storage for alternative power company. Located in Hawke's Bay, one boundary wall was required to be fire rated. Concrete panels were used. Clients' expectations were that after a reasonable size earthquake, they may have to do minor repairs. However, replacing the concrete panel walls due to yielding at the base was not their expectation, and having to repair or replace the steel frame due to yielding was not expected either. Hence, the frame was designed for a ductility of 1, but detailed with ductile capabilities if a larger than code earthquake was to turn up. Panels were simply supported at the base to avoid yielding. The steel frame was fixed base to reduce deflections and hence damage. Rod bracing in the roof, opposite walls were all designed for a Muir 1. Double reinforced panels could have been used. This option was considered, but they would have still yielded at the base, and we would still have had an issue after a large earthquake. The only downside with doing this option was that basically the steel frame needed to be fire rated because it was holding up the panels. So that's the sort of low damage solution that we discussed with the client, and the steel frame was fire rated with a spray composed of gypsum or cement type product. That's it.
Thank you. So this is a new commercial building in Christchurch, and the key driver for our customer for this project was actually getting an anchor tenant. So the original brief our client got was that the anchor tenant wanted a IL2 building, minimum 130% MBS, rated in accordance with the NZSEE guidelines, and we're also told that the client wanted a resilient building. So that caused a few, some discussions. What was even more disappointing, I guess, was the fact that the tenant brief had been prepared by a large, well-respected engineering consultancy firm, which I won't name. So it was a bit disappointing to see the reference to the percentage MBS rating, particularly when resiliency was important. Can you advance the slide. So, as you can imagine, this prompted a bunch of discussions with our client and the tenant and the tenant's engineer, and about how the rating, the percentage MBS rating, is really focused around life safety and has got sort of, well, not that much value in terms of resilience. It's got some. So, and this prompted a whole bunch of discussions with our client and a few others, and we ended up at the end of a few meetings to go run with a 250-year return period damage control limit state event. And this return period was arrived at after we did a benchmarking study with the client and the tenant and their engineer. We looked at other buildings around Christchurch, such as the Christchurch Centenary Library, the Christchurch Convention Centre, and also the MOE guidelines, and everyone seemed to agree that was a reasonable place to be. We then also introduced a drift limit to sort of mitigate some damage to the facade and the partition walls. And then we used, once we finished the design, we then did a bit of an assessment of it to make sure that we could reach 130% MBS as defined by the engineering assessment guidelines. And the structure was fine, apart from the fact we had to make the moat a bit bigger for the isolation system.
Well, thank you all. There's a lot of different interesting thoughts coming out of those various presentations and a wide range of different sorts of building sizes, regional as well as urban parts of New Zealand. But it prompts several thoughts in my mind, one of which is, are our codes set at an appropriate level, which of course is what we're trying to explore with this project, the Resilient Buildings project. But from our point of view, in structural engineering land that we're all working in, I guess the obvious question for all of us is, are we having conversations about building performance expectations with our clients? And what are our clients' expectations? So before we go, and I see we have a bit of time for discussion and questions, let's throw it open and have a bit of a conversation about this, because I think it's a really important topic.
Yes, agreed. Oh, sorry, but that's a bit loud. Back off a little. So, hands up, first question. Catch the ball.
Helen, before we have conversations about whether our codes are at the right level, and with respect, could I ask that you remove that first slide of the June 16th aftershock failure, because that building design wouldn't have met any code. It was just a complete shambles. It didn't meet the codes before the May 2011 amendment to the seismicity in Christchurch, and it's just a really bad example. I don't believe our codes pre the Canterbury sequence are as broken as a lot of commentators say they are. A lot of the time it was how they're interpreted and how hard they're pushed. So, yeah, I think this discussion on resilience and getting better buildings is absolutely vital, and we need to move forward. But I think we're still pretty well served by the basic suite of codes in this country, if they're used correctly.
You're making a really good point. I am aware that building has been somewhat challenged in terms of being reviewed based on its performance, but it raises the point that that's what the public are seeing.
Yeah.
And so, unfortunately, we are dealing with two things here, one of which is, are the code as when we're doing great work, and almost always we are, but we've also got the challenge that we have these outliers and that's informing public opinion as well. Yeah. And so we've got a really interesting challenge, and I thought that Paul's comments and Michelle's comments earlier were really pertinent for this discussion. And we've just got to think about all of these aspects. But I agree with you. It is that particular building, unfortunately, had a number of issues that have been later identified.
The fact that the media gave one of the designers, some airtime, and I think he's quoted early on saying, "Oh, it's impossible to design anything to, stand up to this earthquake sequence," didn't help, and that's what the public latches onto. Little things that we can do, and just jumping in, sorry, I'm talking too much? Or, again, talking about shear keys for the frustration is that even trying to get shear links into those waffle slabs, we're still striking it that, you know, we just put them in as a matter of course and get pushback. Well, firm X and Y, you know, don't make us do that. It's a pain in the arse to put in, let alone getting shear keys in. So if everyone just, you know, nickel and dime stuff, if everyone just lifted the bar a bit, it'd be a whole lot easier. That's enough.
Michelle, you going to comment?
Yeah, I agree with what he said.
All righty. Okay, we've got a question over here. Excellent. Look at that. Nice throw.
With a bit of discussion throughout this whole session around resilience and low damage design systems, can anyone offer any commentary on that might have come from the insurance sector as to whether there'd be positive impacts or, you know, benefits from an insurance perspective by incorporating a damage control limit state or a low damage design system into your projects?
I can answer that a little bit. So we had a gentleman from the Insurance Council, I forget his name, but in reference to Wellington, he was saying it's not a question of getting maybe a discount on your insurance. It could be a question of whether you get insurance or not. Was the response that we got.
Thank you.
Maybe just add the discussions I've had, my understanding is the insurance industry are evaluating things on a regional level, not on a building level. And that's a bit of a problem because obviously we do things on a building level and one of the big paybacks should be to a client on the insurance side, but there's a mismatch between how we approach buildings and how they do. And I think anybody who's got ties into them, you know, do what you can to stimulate that conversation, because until that can get addressed, I think we will continue to have a bit of a mismatch, but hopefully in time we can address that.
One of the things that we are asking in these interviews, as we're talking to people that are building owners and much wider sectors of society than just tenants and building owners and those that have got an interest in the construction, but we've also got to respond to people that use buildings in a wider sense. But we're asking people, think of in the future, 20 years' time, and there is no insurance, because that actually, if we're not careful, could be an outcome. And so we need to think about that, and I think we've often had clients who have rather assumed that insurance will fix everything, and so that's something that we probably want to explore a little bit.
Okay, time for another question. Oh, way back over here, so it's going to be a double chuck, I imagine.
Who's going?
Go for it.
Thanks. My question was, a lot of your discussions were around your clients' expectations, but the question I thought was, what was the public's expectations of buildings and performance? And quite often the client has nothing in common with the general public, and you have property developers who want the cheapest possible product and then 2 years later dispose of it to investors who might have these expectations but get sold something completely different. And unless it's actually sort of addressed in like codes, then I don't think it's something that will really ever take off, because you're selling buildings to developers unless you're working for the government.
You're always going to have developers who are going to want to scrape through the bare minimum of acceptable to code. I agree. Until we, in general, raise the bar. It's quite tricky, and it's something that we struggle with. You have some clients that you work for, and I suppose you can be a little bit selective about what clients we do work for, which is a good thing in the current market. And it's nice to work with clients who are long-term building owners who actually want to invest in their assets and want to talk about low damage design and what things will look like after an earthquake. But having said that, even from these people I do hear, we're still insured. If it gets damaged, I'll fix it after, and then insurance helps pay for it. So you're 100% right, though. Until there's a legal requirement, some people just won't embrace what we're talking about.
Yeah, I think it's probably the majority.
My personal opinion on this matter is that there's probably a greater education piece that generally needs to go out. I'm not sure whether you guys would agree or not, but when I go about explaining to the general members of the public or clients for that matter on how structural engineers go about designing buildings, and I explained to them that there are two states, serviceability limit state and ultimate limit state. They're like, well, okay, I've never heard of that, but fine. And I say to them that serviceability limit state is around ensuring that your facility remains effectively free from damage. And they're like, yep, okay, I like that. And then I explain ULS, saying this is about life safety, and that anything post SLS, technically speaking, is about life safety. And they're like, oh, okay. And then I explained to them that the return period for an SLS event for buildings less than IL4 is 1 in 25. And the likelihood of, as I said earlier, an SLS level event occurring within a building lifespan of 50 years is just shy of 90%. We're effectively saying that any building within that time frame is likely potentially to require repairs. And then that's where they say, well, I don't want that. I want a greater resilience, please. And I think this is where our code and the communication that we have and the education that we're giving out perhaps does not marry, and that we could improve there.
Yeah, I'd echo that as well. One of the best things I've ever managed to find to say to a client to get them to act is tell them about the SLS1 condition and tell them that it's got about an 80% probability of exceedance over the life of a building or something like that. It's really high when you start looking at it. Is that right? Anyway, it's a very high number when you look at it. And most of them have no idea. And when you tell them about that, they really don't like it. And if you start presenting some of the numbers as well over 7-year investment life cycles and the probability of exceedance, the numbers get quite scarily high for them, and they actually start to consider these things. So I think with owner-occupier type clients, then that will help the discussion. I think with the general public, it's very unlikely they're going to engage with that, and it needs very simple tools. I'm hoping the low damage design guide and yes, it meets that will be one of those tools that might start some of that change.
Cool, thanks. I think we've got time for one last question, if anyone wants to ask one more. Excellent. We don't have to chuck it too far. All good.
Everyone talks about the 50-year design life, but isn't that inherently a little bit silly? How many buildings really are demolished after 50 years? I mean, you live in a 100-year-old house, so should we not be thinking about probabilistic performance in a slightly different context, where these 50-year lifespans are just totally arbitrary?
I would totally agree with that. Absolutely.
Looks like we all agree. That's one of my favourite points too, and I'm not even on the panel. Yeah, all the buildings I look at are way over 50 years old. Okay, I'm just going to close it out there. Could I first ask you to thank all our speakers for this final session?